You have never seen Earth, not really. Every photograph, every satellite image, every spinning globe on your desk is a lie. The planet beneath your feet right now is not a sphere. It is not even close. And the method scientists use to reveal its true shape. They measure something completely invisible. Gravity, not with their eyes. Not with cameras. With the silence between two falling objects. For 3 centuries, we assumed Isaac Newton had solved the problem. A spinning ball, slightly flattened at the poles. Simple geometry. Case closed. But Newton was wrong, not about physics. About the shape itself. Earth is lumpy. Dented. Bulging in places no one predicted. The Himalayas pull satellites toward them. The ocean above Iceland sinks lower than it should. Antarctica's ice sheet warps spacetime itself, bending the paths of everything that flies overhead. And here is what makes this personal: the ground you are standing on right now is not where you think it is. Your GPS assumes a perfect mathematical ellipsoid. Reality is different. The true surface of Earth, the shape defined by gravity alone, deviates from that perfect model by nearly 100 meters in some locations. 100 meters. That is a 30-story building of error, hidden in plain sight. So how do we map something we cannot see? How do scientists measure the shape of a world using a force that has no color, no texture, no sound? The answer launched in 2002. Twin satellites, flying in formation, separated by exactly 220 kilometers. Their only job: fall toward Earth together, and measure the microsecond differences in how fast they fall. The mission was called GRACE. Gravity Recovery and Climate Experiment. And what it revealed changed everything we thought we knew about planetary science. Dr. Byron Tapley, the mission's principal investigator at the University of Texas, described the concept with disarming simplicity. 2 satellites chasing each other through space. When the lead satellite passes over a region of stronger gravity, it accelerates slightly, pulling ahead. When gravity weakens, it slows down, and its twin catches up. The distance between them, measured to within 1 micron, less than the width of a human hair, maps the invisible architecture of mass below. But GRACE was just the beginning. What scientists discovered was not merely a better map. It was a window into Earth's interior. Into its oceans. Into its ice. The shape of a planet, it turns out, is not a fixed answer. It is a living question. Constantly shifting. Responding to forces we barely understood. By the end of this journey, you will know how scientists measure the shape of worlds they have never touched. You will understand why Saturn is the flattest planet in our solar system, why Mars carries a gravity scar the size of a continent, and why the Moon's lopsided bulk tells the story of an ancient cataclysm. You will learn the difference between the surface you see and the surface gravity defines, a distinction that matters for every satellite in orbit, every ocean current on Earth, and every spacecraft navigating the outer solar system. And you will discover why the question, what shape is a planet, does not have a single answer. It has layers. Each one stranger than the last, the invisible geometry of worlds. Mapped by falling machines. Revealed by silence. Let's begin. The first person to prove Earth was not a perfect sphere never left France. In 1735, The French Academy of Sciences launched 2 expeditions to opposite ends of the world. One team traveled to Peru, near the equator. The other to Lapland, inside the Arctic Circle. Their mission: measure the exact length of 1 degree of latitude in each location. If Earth were a perfect sphere, both measurements would be identical. They were not. The Arctic degree was longer. The equatorial degree was shorter. Earth, the data proved, bulged at the equator and flattened at the poles. Newton's prediction, made 50 years earlier from pure mathematics, was confirmed by men with wooden surveying instruments, trudging through jungles and snowfields. But measuring Earth from its surface had limits. For 2 centuries, geodesists, the scientists who study planetary shape, relied on triangulation. Climbing mountains. Stretching chains across valleys. Calculating angles between distant peaks. By 1900, they had mapped Earth's flattening to remarkable precision, 1 part in 298. The planet's equatorial diameter exceeded its polar diameter by approximately 43 kilometers. Case closed. Again, then came satellites. And everything fell apart. In 1958, the United States launched Vanguard 1. A grapefruit-sized sphere with solar cells and a radio transmitter. Its scientific purpose was almost an afterthought. But as tracking stations followed its orbit month after month, something unexpected emerged. Vanguard was not following the predicted path. Dr. John O'Keefe at NASA's Goddard Space Flight Center analyzed the discrepancies. The satellite's orbit was being tugged by gravitational anomalies no ground survey had ever detected. O'Keefe published a controversial conclusion: Earth was slightly pear-shaped. The southern hemisphere bulged outward more than the northern hemisphere by approximately 15 meters. The geodesy community resisted. 2 centuries of ground measurements had shown no such asymmetry. How could a tiny satellite see what thousands of surveyors had missed? The answer was profound. Ground measurements mapped the visible surface, mountains, valleys, coastlines. Satellites mapped something else entirely. They responded to mass, to density, to the invisible architecture of rock and metal thousands of kilometers below the crust. This was the first major complication. The shape scientists could see and the shape gravity defined were not the same thing. Consider the ocean. Water flows downhill. It seeks the lowest point. But downhill is defined by gravity, not by geometry. If you removed all currents, all winds, all tides, the ocean surface would settle into a shape called the geoid. A surface where gravity is equal everywhere. Where a ball placed anywhere would not roll. That surface is not smooth. Dr. Maria Zuber, planetary scientist at MIT, describes the geoid as the shape Earth would have if it were entirely covered by a calm, connected ocean. It rises over dense regions. It sinks over mass deficits. Above the Mariana Trench, the geoid dips nearly 105 meters below the mathematical ellipsoid. Above Iceland, volcanic rock pulls it upward. The geoid is Earth's true gravitational shape. And it looks nothing like a globe. By the 1980s, satellites had revealed hundreds of these anomalies. But resolution remained limited. Scientists could see the broad strokes, the continental scale bulges and depressions. The fine details, the gravitational fingerprints of glaciers and aquifers and tectonic motion, stayed hidden. They needed something more precise. Something that could measure gravity changes smaller than 1/1,000,000th of Earth's pull, but no one expected what came next. The problem was not building a more sensitive instrument, the problem was that gravity itself refused to stay still. In 2002, NASA and the German Aerospace Center launched GRACE. Those twin satellites, separated by 220 kilometers, began their silent chase around Earth. Every month, they produced a new gravity map. Scientists expected refinement. Small corrections to the geoid. A cleaner picture of the same stable shape. What they got was chaos. The first monthly map looked different from the second. The second looked different from the third. Gravity was shifting. Not over millions of years. Over weeks. Dr. Isabella Vellicogna at the University of California, Irvine, was among the first to understand what GRACE was seeing. The satellites were not measuring rock. They were measuring water. When monsoon rains flooded the Ganges basin, gravity increased over India. When groundwater was pumped from California's Central Valley, gravity decreased over the American West. When ice sheets melted in Greenland, the gravitational tug of the entire region weakened measurably from space. The shape of Earth was breathing. This was the turn. The moment that shattered 2 centuries of assumption. Scientists had treated planetary shape as a fixed property. Something you measured once, refined occasionally, and printed in textbooks. GRACE revealed the truth: shape is a process. A continuous response to mass in motion. Water cycles. Ice dynamics. Even the slow creep of mantle rock thousands of kilometers below the surface. Dr. Byron Tapley, who had spent decades designing the mission, described the shift in thinking. Geodesy was no longer about mapping a static world. It was about watching a planet change in real time, but not everyone agreed on what the changes meant. A scientific debate erupted. GRACE showed Greenland losing approximately 280 billion metric tons of ice per year. Antarctica appeared to be losing mass too, but the signal was complicated. Some regions gained ice while others collapsed. Dr. Eric Rignot at NASA's Jet Propulsion Laboratory argued the losses were accelerating. Other researchers questioned whether the satellite pair could truly separate ice loss from deeper geological motion, the slow rebound of crust still rising from the last ice age. The instruments were precise. The interpretation was war, and then GRACE revealed something no one had predicted at all. In 2004, a magnitude 9.1 earthquake struck the Indian Ocean. 230,000 people died. The seafloor shifted. Tectonic plates lurched. And GRACE, flying silently overhead, recorded the gravitational signature of the event. The earthquake had changed Earth's shape. Not metaphorically. Physically. The redistribution of mass altered the planet's gravitational field permanently. Scientists calculated that the event shortened Earth's day by 2.68 microseconds. The axis of rotation shifted by approximately 7 centimeters. A single earthquake. Measured from space. By the silence between 2 falling machines. The implications rippled outward. If Earth's shape was this dynamic, what about other worlds? Mars has no oceans, no ice sheets cycling water across continents. But it has carbon dioxide glaciers that grow and shrink with the seasons. It has dust storms that redistribute mass across hemispheres. Does Mars breathe too? Saturn's moon Titan has methane lakes. Europa has a subsurface ocean. Enceladus vents water into space. Every world with moving mass has a shifting shape. A living geoid. A gravitational heartbeat, and measuring that heartbeat became the key to understanding planets we may never touch. The breakthrough came from a world without oceans. In 2012, NASA's Grail mission entered lunar orbit. Two spacecraft, nearly identical to Grace, began their gravitational waltz around the Moon. But unlike Earth, the Moon has no water cycle. No shifting ice. No breathing atmosphere redistributing mass. The Moon's gravity field was frozen in time. A fossil record of everything that had ever happened to it. Dr. Maria Zuber led the mission. What Grail revealed was a history written in invisible ink. The lunar crust was shattered. Not cracked in a few places, but pulverized everywhere, down to depths of several kilometers. 4 billion years of asteroid bombardment had fractured the entire outer shell. The gravity data showed density variations too chaotic to explain by simple geology. But the deepest mystery lay on the far side. A basin called the South Pole Aitken, one of the largest impact craters in the solar system, showed a massive gravitational anomaly. Something dense was buried beneath it. Analysis suggested a metal-rich asteroid, perhaps 240 kilometers across, still embedded in the lunar mantle. An ancient impactor that never fully dispersed. The Moon was carrying a scar. And gravity was the only way to see it. Suddenly, the technique that had mapped Earth's breathing revealed its true power. Gravitational measurement could reconstruct the past. Mars demonstrated this next. NASA's InSight lander, combined with decades of orbital tracking data, produced the most detailed gravity map of another planet ever made. Dr. Bruce Bannard, the mission's principal investigator, described what emerged: a world frozen mid-transformation. Mars has the largest volcanic structure in the solar system. Olympus Mons rises 22 kilometers above the surrounding plains. But the real revelation was beneath it. The volcano's mass had warped the Martian crust so severely that the entire planet bulges outward in that hemisphere. Mars is lopsided, permanently deformed by its own geology. And on the opposite side of the planet, the Hellas Basin, a colossal impact crater, represents a mass deficit so profound that spacecraft passing overhead accelerate measurably as gravity weakens. The synthesis became clear: shape is memory. Every planet carries the gravitational record of its formation, its impacts, its internal evolution. Earth's geoid remembers the mantle plumes rising from its core. The Moon remembers the bombardment that nearly destroyed it. Mars remembers the volcanoes that reshaped its crust and the impacts that excavated its basins. To measure shape is to read history. Dr. Carol Raymond, deputy principal investigator on NASA's Dawn mission, applied this principle to smaller worlds. The dwarf planet Ceres, orbiting in the asteroid belt, showed a gravitational signature inconsistent with solid rock. The data suggested a partially differentiated interior, with denser material concentrated toward the core. Ceres may have once had a subsurface ocean. The gravity field preserved the evidence. But open questions remain: why does Earth's geoid change so rapidly in some regions and remain stable in others? What drives the deep mantle flows that create gravitational anomalies lasting millions of years? And as ice sheets collapse and aquifers drain, how will Earth's shape evolve over the coming century? The instruments are ready. GRACE Follow-On, launched in 2018, carries laser interferometry precise enough to detect changes smaller than a single virus. We can now watch a planet reshape itself in real time, but the real question is not what we found. It is what it means. You have never seen Earth, but now you understand why the planet beneath your feet is not a shape. It is a story, written in the language of mass and motion, told by the silence between falling machines. And the scientists who learned to read that language discovered something profound. Every world whispers its history through gravity. The implications reach far beyond cartography. When engineers calculate satellite orbits, they no longer use a simple ellipsoid. They use gravity models with millions of terms, capturing every ripple and depression in Earth's invisible surface. Without this precision, GPS would drift by meters. Spacecraft would miss their targets. The International Space Station would require constant correction just to maintain altitude. When climate scientists track ice loss, they do not rely on photographs alone. GRACE Follow-On measures the mass directly. The data shows Greenland losing ice 6 times faster today than in the 1990s. Antarctica's contribution to sea level rise has tripled in the same period. These are not estimates from models. They are measurements of gravity itself. When planetary scientists design missions to distant moons, they plan for gravitational reconnaissance first. Europa Clipper, launching soon, will map the gravity field of Jupiter's ocean moon during dozens of close flybys. Variations in that field will reveal the depth of the subsurface ocean, the thickness of the ice shell, and whether the seafloor might harbor conditions suitable for life. Shape is no longer description. It is detection, and the technique keeps evolving. Future missions propose gravitational mapping of Titan's methane seas, of Enceladus's erupting plumes, of asteroids that may one day threaten Earth. Each measurement adds another layer to our understanding. Each world becomes a text we can finally read. Dr. Maria Zuber, reflecting on 3 decades of gravitational science, put it simply. We used to ask what planets look like. Now we ask what they are made of, how they formed, and whether they might harbor conditions for life. Gravity gave us the tools to answer. But there is something deeper here. Think about what this means for you. You live on a world that is constantly reshaping itself. The ground rises where glaciers retreated 10,000 years ago. The ocean surface dips and swells with the density of rock below. Your own weight, the gravitational pull between your body and Earth's mass, is not constant. It varies by a fraction of a percent depending on where you stand. You are embedded in a gravitational field that connects you to every mountain, every ocean trench, every molten current in the mantle below. The force that keeps your feet on the ground is the same force that reveals the shape of worlds billions of kilometers away. Carl Sagan once wrote that we are a way for the cosmos to know itself. Gravitational science takes that insight literally. We have built instruments that feel the shape of planets through the fabric of spacetime itself. We have learned to see with a sense we do not possess, translating invisible forces into maps, into histories, into predictions of futures we may yet prevent. The invisible geometry of worlds. Mapped by falling machines. Revealed by silence and now, revealed to you the next time you look at a globe. Remember, you are seeing a symbol, not the truth. The truth is stranger, more dynamic, more alive. Layers upon layers, each one a chapter in a story still being written. The universe measures itself through gravity, and so, now, do we.